Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through Markov chains. So let's start with an example that would lend itself to a Markov chain. So let's say I go to a casino or something and start with $1 and I make a series of $1 bets against the house regarding whether a coin comes up heads or tails. So if it comes up heads, I win $1. And if it comes up tails, I lose $1. And let's say that I keep doing this over and over until either I run out of money, so I'm back at $0 and ruined, or I get up to $5 and then I decide to cash out. So I'm going to put this into a diagram. So what I have here are 6 possibilities for the amount of money that I have. I can have anywhere from $0 to $5, only integer values. So I started here at $1. So if I win, then I now have $2. So the probability of going from 1 to 2 is 50%. Now then if I get $2, my probability of going from $2 to $3 is 50% or 0.5. But of course in both examples there's a possibility I go back. If I have $1, there's a 0.5 probability I lose and go back to 0. Similarly, if I have $2, probability is 0.5. So let's now go through and put in all of these arrows. So I also need some arrows on 0 and 5. If I have $0, I'm going to stay there with probability 1. Similarly for 5. So I call each of these black things 0 to 5 states. So this is a Markov chain with 6 states. And that's sort of what Markov chains do. They identify some states and we look at the probability of going from one state to another. And we're usually interested in what's the probability will be in a given state after a certain period of time. Of course, states can mean so many different things. You know, we can have a state meaning living in the city and another state living in the suburbs. And we can look at the long run trend of how many people will be living in the city and in the suburbs after a certain amount of time. So states don't have to be numbers. So this is a discrete Markov chain because you can see here there are only 6 states, but the time here is also discrete. We're going to be looking at the probability of being in a state after I've played the game once, after I've played it twice, 3 times, and so on. Markov chain also needs a transition matrix P. So where P, so this is supposed to be a little p, P sub ij, so that's the element in row I, column j of this matrix, is equal to the probability that I go from state I to state j. So the states here need to be numbered. So because we can't have row 0 or column 0 in a matrix, I'm going to say that this is the first state, 1 is the second state, and so on. So I set up my transition matrix like this. It will be a 6 by 6 matrix because there are 6 states. So the first row corresponds to if we're in the first state, what's the probability we go to each of the other states. So the 1, 1 entry is the probability that if we're in the first state, we stay there. So in this diagram, that's 1. We know we're going to stay there. That's certain. So there's no chance that we could go to the second, third, fourth, fifth, or 6th states. So the next row corresponds to the second state. There's a 0.5 chance we'll go back to the first. No chance we'll stay where we are. There's a 0.5 chance we'll go to the third state. But there's no chance that we can get to the 4th, 5th, or 6th states in one step from the second state. So we do similarly with rows for the other states. So what should happen when we're setting up our matrix in this way, the sum of the entries in each row should add to 1, because probabilities add to 1. In this case, we say that P is a row stochastic matrix. So you can also have matrices that are column stochastic. In fact, some textbooks, when they're doing Markov chains, will have the columns, the entries of the columns adding up to 1. It doesn't really matter. I'm just using rows because I think that's more natural for this rule here. So we also need an initial distribution. So that tells us the probability we start in given states. So our initial distribution for this Markov chain is pi, as written on your screen, because I told you we start with $1. So note that if p is row stochastic, our probability distribution needs to be a row vector and needs to be a probability vector. So all of its entries need to add to 1 because probabilities always add to 1. So the probability will be in given states after we play this game once can be easily calculated. So if I multiply pi by the transition matrix P, I will get another row vector, and it turns out it will also be a probability vector. So pi P tells us what we can pretty much figure out already. If I start with $1, after playing the game once, there's a 50% chance I will have $2 and 50% chance I will have $0. So you've got to figure that out very, very easily without a Markov chain. But where Markov chains help is when, say, we play this game many times, what would be the probability we're in each of these states? So let's say we've played it 6 times. So to figure out the probability will be in each state, we calculate pi times p to the power of 6. So we probably want to use a computer for this. So this is what we get if we times pi by p to the power of 6. We get this string of 6 numbers that adds up to 1, corresponding to the probability we're in each state. So there's a 68.75% chance that I've gone broke and I've stopped playing after 6 goes, or within the first 6 goes. There is a probability of about 0.08 that after 6 goes, I will have exactly $1 left. And of course, there's no chance that I will have only $2 left, and so on. Without the Markov chain, I wanted to calculate this here. I wanted to calculate the probability that I have exactly $3. So that's actually very tricky. We know that if we started with $1 and we had $3 after 6 goes, I must have won 4 times and lost twice. That's how I'd end up with $3. So we'd be looking at the probability of combinations of winning 4 times and losing twice. But not all combinations would be valid. For example, I can't have lost the first 2 and then won the next 4. That's invalid because if I lost the first one, I would go back to 0 and I would stop playing. So we can't include all combinations. So our normal probability calculations wouldn't help with this, and Markov chains make it so much simpler. So another question we might want to ask is what will happen in the long run? Now, it's probably clear for this chain, but I want to show you how we would do that anyway. So I'm going to rub out most of what's on the screen. Please pause and copy down if you need. So the diagram that had all the states and arrows and its probabilities is called the accessibility diagram. Turns out that if I have the transition matrix P, that's really all I need to know about the Markov chain. Now I want to digress just to make some generalizations about row stochastic matrices. So I'm going to explain it for the 3x3 case, but this can be generalized to any n by n case. So let's say I have P, and P is a row stochastic matrix. So it turns out it always has an eigenvalue of 1. So why is that? Well, it turns out if you multiply this by the vector 1, 1, 1, the vector of all 1s, you get this. But note that A1 plus A2 plus A3 is 1 because this is a row stochastic matrix. The entries in each row add to 1. So this is just equal to 1, 1, 1. So that means we've multiplied by a vector and got back that vector. So 1 must be an eigenvalue. Now, if 1 is an eigenvalue of P, it must be an eigenvalue of P transpose. And that's because a matrix and its transpose have the same determinant, and so they'll have the same characteristic polynomial. So why am I telling you all this? Well, let's say I want to find an eigenvalue and an eigenvector for this Markov chain. So because of what I said, we're actually using row vectors. I actually want to find a left eigenvector. Now, if I want to find the eigenvector corresponding to eigenvalue 1, I'm solving this equation pi p equals pi. Now, because we're used to finding row eigenvectors, what I can do is I can transpose this equation. So to find the eigenvector of my row stochastic matrix that corresponds to eigenvalue 1, I go and find the eigenvector, the right eigenvector, the same way we've been doing all this time. We find the right eigenvector of P transpose. So why am I obsessed with this eigenvalue of 1? Well, it turns out that 1 is the largest eigenvalue of any row stochastic matrix. Any eigenvalue not equal to 1 is less than 1 in absolute value. I should point out, however, in this case and in other cases, the eigenvalue of 1 can be repeated. It can have an algebraic multiplicity greater than 1, so there may be more than one eigenvector associated with it. But remember when we were doing discrete dynamical systems, we had this. Remember what we did is we decomposed the initial vector x into a linear combination of the eigenvectors v1 to vn of A. So as k approaches infinity, it gets larger and larger. Any of these eigenvalues that are less than 1 in absolute value, they will tend to 0. So if this eigenvalue, for example, was 0.8 for sufficiently large k, this term would drop out because it would be close to 0. And what we would be left with is just a linear combination of the eigenvectors corresponding to eigenvalue 1. There's always at least one eigenvalue 1. So of course 1 to the power of k, no matter how large k is, that's just 1. So if this matrix, for example, had only one eigenvector corresponding to eigenvalue 1, we'd just have A to the power of kx is equal to some multiple of that eigenvector. And the same thing works if x is a row vector instead of a column vector. I just wrote it like this because this is what we did in discrete dynamical systems. So why am I going through all this? I'm just explaining to you why. If I want to know the long-run behavior of the Markov chain, what I do is I find the eigenvector corresponding to eigenvalue 1. So remember, because we're using row vectors instead of column vectors, what I'm going to do is actually find the eigenvector of P transpose. So I'm going to show you how to do it for our transition matrix here. So for the matrix, I simply solve the equation pt minus 1i, or just minus I, because I am looking for the eigenvector corresponding to eigenvalue 1, times some vector x transpose equals the 0 vector. So this will allow us to make it into a right eigenvector problem like we've solved millions of times before. So what we end up getting is this. So it turns out that the eigenvalue 1 has both algebraic and geometric multiplicity of 2. But what this is telling us is essentially common sense. We know that the chain is eventually going to end up in the first state where I have $0 and I'm ruined, or it's going to end up in the last state where I have $5 and cash out. We can't say for sure which one we will end up in. So note that this was totally independent of the initial distribution. I didn't actually refer to pi in this calculation. So no matter the state in which we start, we will always either end up in state 1 or state 6. We'll end up with $0 or $5. One might be more likely than the other depending on where we start, but we can't say for sure which of those states will be the one in which we end up. So for this Markov chain, we actually say it doesn't have a steady state distribution, because if you like, there's sort of two steady state vectors and we can't say for sure which one will be the limiting distribution. So this is an example where there's no steady state distribution. In fact, both of these vectors constitutes a stationary distribution, but not a steady state distribution. So let's look at an example of a Markov chain where there absolutely is a steady state distribution. This transition matrix is for a Markov chain with two states. So I said E for employed is the first state and U for unemployed is the second state. So what is this transition matrix telling us? It's saying 98% of the people who are employed now will still be employed the next time we recalculate the probabilities. 2% will have lost their job. Maybe they quit, retired, whatever. And then the second row tells us that of the people who are unemployed, 5% of them will become employed at the next time interval, and 95% will remain unemployed. So let's say we're doing this by months. So if this is our transition matrix P, we need to start with some initial distribution, and we can calculate the proportion of people that will be employed or unemployed after a certain number of months. So if we want to know, what that will be after k months, we simply calculate pi times p to the power of k, where pi is the initial distribution. So that's easy to do, but let's actually calculate what happens in the long run, which actually doesn't rely on an initial distribution. So once again, we want to find the eigenvalues associated eigenvectors. But remember what I said, a stochastic matrix like this always has largest eigenvalue of 1. All other eigenvalues are less than 1 in absolute value. So all we need to do is find the eigenvector of this matrix corresponding to eigenvalue 1. So remember, what we really want is a row eigenvector. So because we've only been dealing with column eigenvectors, what we're going to do is once again solve P transpose. We're going to find a column eigenvector of P transpose. So we solve P transpose minus I times some vector X transpose is equal to 0. Again, you can use a calculator for this. Turns out that an eigenvector we get is 2.51. So this can't be the right answer. It's not a probability vector, because remember, a probability vector, its entries need to add up to 1, and all of its entries need to be non-negative. But remember, if V is an eigenvector of a matrix A, any scalar multiple of V, the eigenvector, will also be an eigenvector. So all we need to do is divide both of these by their sum. 3.5 plus 1 is 3.5. I just divide each entry by 3.5, and I get 5 over 7, 2 over 7. So what that means is, in the long run, it's going to settle down to this distribution, 5/7, 2/7. So in the long run, what will happen if this situation keeps happening, the situation described in the transition matrix, 5/7 of people will be employed and 2/7 will be unemployed. So at that distribution, the number of people who are unemployed, who become employed, will be equal to the number of people who are employed that become unemployed. So the change in the number of unemployed people will be 0. The change in the number of employed people will be 0. Once again, this is independent of the initial distribution. It doesn't matter whether there were 80% of people originally employed or there were 30% of people originally employed. Over time, in the long run, this will be where the chain ends up. So what that's saying mathematically is that as k approaches infinity, pi times p to the power of k will approach this vector here, regardless of the row vector pi, as long as it's a probability vector. So in this case, there was only one vector associated with eigenvalue 1, so this is the steady state vector. So that means at some point, this will be the probability distribution of employed versus unemployed, and all subsequent times after that, it will stay at this distribution. All right, thank you so much for tuning in to this video. This has been the luckiest maths teacher in the world. Have a great day.